먼저 그 웨어러블 테크의 그 선두주자죠. 송구적 인식 기술 서비스인 MYO를 개발한 탈믹 랩스, 스티븐 레이크 순서입니다. 탈믹 랩스는 캐나다 소재의 그 워털루 대학생 3명이 2012년 5월 창업한 회사로 현재까지 스파크캐피탈, 그 다음에 인텍캐피탈로부터 약 170억 원 정도 투자를 유치했고요. 그리고 정말 바쁜 일정에도 불구하고 멀리서 컨퍼런스를 위해 참석해주신 스티븐한테 다시 한번 감사를 드리고, 또 스티븐은 너무 바쁘기 때문에 끝나자마자도 다시 캐나다로 출국할 예정입니다. 그러면 스티븐을 모시도록 하겠습니다. 네, 큰 박수 부탁드리겠습니다.
Thank you very much. I'm really excited to be here in Korea today, all the way from Canada, where Atomic Labs is based, to tell you a little bit about what we call MYO, a new type of human-computer interface. And so I'm going to spend a little bit of time on showing you the technology itself, the device, some of the applications, and also a little bit about the history and why we ended up here today developing this. So, first of all, I'd like to show you one of the actual engineering prototypes here. I'm just going to bring up. So what you're seeing on the screen behind me here is actually a real-time output of my hand here. And so you can see I'm not tethered to this computer. I'm actually wearing this device called MYO on my arm here. And as I make motions with my hand, those are translated, interpreted by this device, and that 3D hand on the screen is actually rendering these gestures. Simple ones here to the left and to the right, to give you that idea. And so I'm going to kind of step back and actually show you how that's possible and how using what it turns out is the muscle activity or the tiny electrical signals from the muscle of my arm, we can detect this information. And so it actually all began in Zurich, Switzerland, where I was studying something called biomedical engineering and working in this area of wearable technology. And at the time, we had been developing a device actually for the blind, and it was a belt-worn device with some sensors in it, and it would detect obstacles in front of the person and translate that into tactile feedback. So it could help the blind, in a sense, regain their sense of sight or see again. And so we asked the question that if wearable technology could be used to help those who are disabled regain some of their abilities or senses, what could it do for the rest of the population? And that got us thinking. And it also brought us to the state of the art in this field of wearable technology and wearable computing in the broader sense. And what we learned is that a lot of work had been done in the past 10, 20 years on the other supporting technologies that make these new devices possible. Things like processing power has increased rapidly. Battery technology has gotten to the point where we can do a lot of stuff right on devices that we're wearing on the body. But what didn't exist was an interface that would enable us to interact with and communicate with these types of new devices when we're no longer tethered to a desktop computer or laptop computer in front of us. So what we wanted was a way that us as humans could interact with the digital world anywhere in this next generation of computers. And we realized that through evolution, we've used our hands to interact with everything around us. We've evolved to do that. Yet the gold standard in human-computer interaction for wearable devices was voice control. And so you walk around talking to these devices in the future. And we felt that that wasn't a good solution. One, voice control is low fidelity. Two, you've got the social problem of being that crazy guy talking to himself down in the corner. And so we set out to devise a way to use our hands to interact with the digital world and basically plug our hands into that virtual or digital space. And we had this question. We said, well, how can we detect that movement? We can't use cameras because we want to be out in the environment, something wearable. How else can we detect all these movements of our hands and fingers? And what we realized is that the muscles in your forearm that are responsible for the movements of your fingers and hands actually generate these tiny little electrical signals. And these signals naturally occur when the muscle is activated. And so we said, I wonder if we could detect those electrical biosignals and use that to detect the movements of your hands and fingers. And so what I'd like to show you here is actually kind of a window into my arm. So this is going to be what we call the raw muscle signals. The medical term for this is electromyography, or EMG. And so EMG is a big fancy way to say the study of the electrical activity of muscles. And what we're seeing here is a stream from the 8 sensors in this device in my forearm. And so you can see as my arm's kind of out here not doing anything, there's not a whole lot happening right there. But if I were to move my hand, let's say, to make a fist, we're seeing nearly all of those muscles around my arm are all activated. But if I make a different motion, say I make a pinching motion with this finger, we're seeing only a couple of the colors there are channels. Or with this finger here, it's different signals I'm making. Or again, if you look to the right, there's several channels activated, or to the left. And you can see visually just that the spatial differences. So each one of these lines corresponds to a different part of my arm or a different muscle. How we might discern what those different gestures and finger movements are actually made of. And what we can do mathematically as well is analyze these in many different ways. So it's not just which channel has a large signal or a small one, but it's things like the frequency component and all these mathematical characteristics we can pull from this data. And so we take this data from hundreds of people, all across populations, different arm sizes, muscle sizes, race, etc. And we end up with this machine learning model built up of different gestures and motions from all different people. And so that when you put this device on, it can know, are you reaching out and grabbing some data and making a fist? Are you tapping your thumb to your index finger to a different finger, your pinky say? And from that information, we can then plug that into the digital world into all different applications. And so we get not only this muscle activity, we also get very precise motion control as well. And so on board here is a 9-axis motion sensor. It's just as sensitive and precise as your wireless mouse would be in the computer. And so we combine this idea of having motion control plus all the gesture or muscle data to now plug that all into all different applications. So I'd like to show you a few different ways that this can be used. So one of the really exciting ones, and I show this today because I think the next talk or 2 talks after me is actually, you're going to see something called Oculus Rift. And the Rift by Oculus is a great new virtual reality device, a new type of gaming. So you'll see shortly a head-mounted display that lets you immerse yourself in this virtual world. But one of the big challenges with technology like virtual reality is interacting with it, or the interface for that. And so one really popular way that MYO is being used by developers and consumers is actually in virtual reality gaming with devices like the Rift. And so it's plugging your hand to take control when you're in this full virtual world. But there's all sorts of ways that it can be used. And so Rift is one way, especially popular we found here in Korea, given how forward we are with gaming here. But another really cool one, and this just sort of emerged as a co-op student we had, was like, wouldn't it be awesome if I could control a helicopter with MYO? And we're like, yeah, well, that could be pretty cool. I like helicopters. So I'd like to show you a little clip of MYO with a helicopter. Let's try this way. So we've talked about gaming, talked a little bit about quadricopters or helicopters. I'd like to highlight another interesting use case for this new type of interface. And so this here is actually a screen from an Apple TV unit. I don't know if anyone's ever used Apple TV, you've probably seen something similar, where you're trying to enter text with a remote control, you know, going right, up, down to get the letter, you know, S, L, Z to enter your Wi-Fi password or something. And so again, this emerged from a developer had an idea and said, well, what if we could use this technology to actually have some kind of motion or free air keyboard? And so I'd like to show you a really early just proof of concept that one of our co-op students pulled together just in a morning to kind of prove another way we could do something like this using MYO technology.
As you can see, Idris just has to rotate his hand slightly to the left or right to change the cursor position. Then he can select a letter by just hovering over it for a short period of time. When he has the correct word selected, he can just lightly snap, and the MYO will pick up the gesture and tell MYO to enter the word.
So, a very early proof of concept, but the interesting thing there is that whole demo was built using what we call MYO API. So MYO API is a way for third-party software developers and hardware developers to plug in this muscle control technology to whatever they're developing. And that little proof of concept there took literally less than 10 lines of code to build. And so a co-op student built this in about an hour and a half in the morning using 10 lines of code and a MYO prototype. And I think that's pretty cool, is this interface enabling all kinds of new and creative applications like that by developers all across the world. And so we made that a core focus internally, is making it as easy as possible for developers to build on top of this new interface layer technology. So we have APIs right now available for Windows, Mac, Android, iOS, and then we've open sourced the software. And this Bluetooth device has an open source API that developers can take and put on all different platforms. So some examples we've seen is ROS, which is an operating system used to control industrial robots. We've seen Unity by game makers, or Ouya, the console maker, developing this as an interface method. And to make sure that we've made it as easy as possible for developers to build on top of MYO, we actually bring in, every week, new groups of developers that have never used MYO before into our office, and we give them kind of the latest and greatest, the latest version of our SDK, the latest features we're experimenting with, and we say, what do you think about this? What can we change? How can we make it easier? And the other way that we get feedback from developers to make it even easier to develop with MYO